Greetings. We will discuss the electron gas in the Jellium potential. We did it in the Hartree-Fock approximation. We did it using perturbative methods. We found that the result in perturbation theory is the same as what you get in the self-consistent field Hartree-Fock method. But then we need to go beyond this approximation, and the approximation that we are going to introduce today is the random phase approximation. And the main references for this are from the article by Rames and Reports on Progress in Physics 1957 and his book Many Electron Theory. And what is done in this model is to treat the electron gas as a plasma. Okay? So, these are the plasma oscillations that you are going to look at. A plasma is often described as a fourth state of matter. It is a highly ionized region as such. There are plasmas in ionized tubes, in gas discharge tubes, as one knows. There is plasma in the atmosphere, in the Van Allen belts, and in various belts of the atmosphere. So, the plasma has a place in many places in nature and even in laboratory. It is a very highly ionized region as such. You have positively charged ions in the plasma, and you also have virtually free electrons in the plasma. The whole system is typically electrically neutral. Now, our picture of the electrons in metal is similar to that of a plasma, because you have got an assembly of positive and negative charges. The whole system is electrically neutral. The positive charges are sort of frozen in physical spaces. So, their vibrations we do not consider at this point. They have far more inertia than the electrons. So, to the first approximation, we can consider them to be frozen in space. Their oscillations are not involved. Although when you consider lattice dynamics and so on, you can always make subsequent corrections, but we begin with the model that the positive ions are frozen in space. But beyond that, we also make the Jellium potential approximation and so on. So, that is something that we have done in the previous considerations. What we are going to do today is to consider oscillations of the electron gas. And I had referred to this picture earlier, that you have got a positive and negative charge in balance. You consider a small displacement of the electron gas to the right, so that you have a net negative charge on the right side of this figure and a net positive charge on the left side. So, there is a net negative charge per unit area, which is minus E rho times I, if rho is the volume charge density, and then you have got a net positive charge per unit area on the left side, which has got the same magnitude, but it has got a positive sign. The surface charge density is E rho xi. This is I am using rho bar to represent the average charge density, because we are going to very soon introduce density fluctuations. Okay? So, I am using the symbol rho bar to represent this charge density, and the net electric field will be the surface charge density divided by epsilon 0. So, that is coming straight from classical electrostatics. This is the net field, and the equation of motion is just mass times acceleration is equal to the force. So, the force is the force per unit area, which is the intensity, times the charge, which is minus E, and essentially you have a simple harmonic motion over here. You have got an equation of motion for the simple harmonic oscillator, which oscillates at a frequency which is given by the square root of this proportionality, which is the spring constant in our usual vocabulary, and this is the frequency of oscillations in CGS units. You will find this relation written more commonly as in terms of the natural frequency omega p. So, instead of this rho e square by m epsilon 0, you get 4 pi rho bar e square by m. Now, what we have done is we are going to ignore thermal motions at this point, except that we assume that some thermal motion would have caused the initial displacement, because you need a origin, some origin. It is not that you have applied an external field to displace the electron gas. Okay? So, this is something which happens internally, but other than that we are going to ignore any thermal motion. So, that is our model. So, in this model you have got the equation of motion for a linear harmonic oscillator, a simple harmonic oscillator. You have the natural frequency of the plasma oscillations given in CGS units. Rho bar is the number of electrons per unit volume. So, this is the number of electrons n. This is the total volume, which is the number of electron times the average volume of each electron, expressed in terms of the average radius of the volume occupied by each electron. So, the n's cancel and you have 3 over 4 pi r cube, rs cube. So, that is the expression for rho bar, which is the average density, and you can put this in the expression for the frequency coming from the solution to this differential equation for the simple harmonic oscillator, and you have this relation. You can see that the 4 pi will cancel and you have got your plasma frequency given by this relation root of 3 e square by m r cube, right, rs cube. Rs is the average radius of the average volume occupied by every electron. So, we have an expression for the frequency of oscillations. We are ignoring dispersion, and when you have dispersion you can make corrections to this term, but that is not the main interest in today's discussion. What we found is the solution to the problem in two approximations. One is the Hartree-Fock, which I write as a superscript here, and in the Hartree-Fock self-consistent field method we found the energy per unit electron to be given by 2.21 by r square minus 0.916 by rs in units of Rydberg, and we got the same solution in using perturbation theory, which I write as a subscript over here. So, both of these gave us essentially the same solution. What we are going to discuss today is go beyond the Hartree-Fock method, go beyond the perturbative method, okay, and introduce an approximation which is known as the random phase approximation. This was introduced by Bohm and Pines in the mid 50s, but I am not going to attempt to give an exhaustive review of the historical development of the random phase approximation, because there are many alternative paths to RPA. You know, it was developed in nuclear physics, it was also developed, there is a Green's function method, there are other methods, and I am not getting into the historical development of this method from various different points of view, but I will specifically concentrate on the method of Bohm and Pines, because it is this method which explains best the term random phase which goes into this approximation. Okay? So, I am going to discuss the Bohm-Pines approach to some extent, and in Bohm-Pines approach you get an improvement over the expression you get either from Hartree-Fock or from perturbative methods. You get additional parameters in terms of beta, which is actually a ratio, and this ratio is Kc over Kf. Kf is our old friend, which is the Fermi momentum in units of h cross, right, and Kc is a certain upper bound to the wave number because oscillations get damped by random thermal motion above it. So, I will explain why you have this upper bound. So, you will have an electron gas in certain state of oscillations of the plasma. So, these are the collective oscillations of the electron gas. These are not the individual oscillations about an electron around a certain equilibrium point, but the collective oscillations of the electron gas, and you will also have a 0 point energy of the plasma oscillations just the way you have it for a simple harmonic oscillator. So, let us develop this model now. You have the quantum field operators psi and psi dagger. These are expressed in terms of the electron creation and destruction operators, which we introduced in an earlier class. Using these, you can write the Hamiltonian, the electronic Hamiltonian, in two equivalent forms, one in terms of the field operators psi and psi dagger, or equivalently in terms of the creation and the destruction operators, the Ci dagger and the Cj, and you have the same over here. You have the two center integral. So, we have dealt with these terms earlier. So, you can express the Hamiltonian in these two equivalent forms. However, we did not specify the spin label explicitly in this. Okay, it is already sitting over here because Q is a set of 4 variables, the 3 spin coordinates and 1 spin variable. So, we will now write these operators explicitly inclusive of the spin labels. So, let us do that. So, having spelt out the spin label as sigma, so you have got 2 operators over here, A1 and A2, correspondingly you have got sigma 1 and sigma 2, and these are then the commutation or anti-commutation relations appropriately for bosons and fermions. For fermions, you have got the anti-commutation relations for the creation and destruction operators. For bosons, these are the commutation relations. And we will be dealing with the anti-commutators because the particles of our interest are electrons, and the field operator now must be written explicitly in terms of a summation over the spin index alpha. So, Ci alpha is the destruction operator for the state I and the spin eigenvalue alpha. Okay? So, these are the good quantum numbers inclusive of spin, and you can write the Hamiltonian, which we had written without explicit indication of the spin label, but now inclusive of explicit spin labels, we can write this Hamiltonian. So, this summation over Ij is over the 1 electron states, and then there is an explicit summation over the spin labels alpha beta. So, the Ci alpha dagger and Cj beta are the corresponding creation and destruction operators. So, it is the same Hamiltonian, but now we have written it fully explicitly inclusive of the spin labels. We can also write it equivalently in terms of not just the field operators, but only in terms of the creation and destruction operators. So, these are completely equivalent forms which we saw in the previous slide as well. So, our notation is well understood that the label Q is a set of 4 coordinates, 3 space coordinates and 1 spin coordinate. Okay? This is the same notation that we used in the Hartree-Fock theory also. Then you have got the particle density operator, which is psi dagger Q psi Q, right? And when you integrate this particle density operator, you will get the total number of electrons, but you must integrate over all the space coordinates and also sum over all the spin labels, because now we have chosen to indicate that explicitly, and you can easily see that these expressions and this notation is appropriate, because if you Now insert a delta function and carry out this integration. This delta function is the product of the delta function for the space arguments and the Kronecker delta for the spin, because the spin coordinates are discrete. So you can now separate the summation over the spin over here, followed by integration over the space coordinates, right? And if you contract these summations, you get essentially the particle density. So this is the particle density which we began with, right? So this is the notation that I will be using. Okay, so this is our particle density operator. What we are going to do is to develop an equation of motion for the particle density operator, because we will essentially be led to density fluctuations in the electron gas. So you can see that this particle density operator is essentially a sum of the Dirac deltas, because if you integrate this, then on the right hand side you will get essentially the total number of particles. So the particle density operator is essentially a summation of the Dirac delta. Okay. You can also use a Fourier expansion of the density, and in this rho k is a Fourier transform, and this is the Fourier expansion of the particle density operator. Notice that 1 over volume comes explicitly over here. So this rho k, the Fourier transform, will be a dimensionless quantity in our notation. Okay. So this is our particle density expansion in terms of its Fourier components. What we have done is to smear the positive charge throughout this box at a uniform density. So now you also have the electron-electron interaction, which we have expressed earlier in terms of all of these, this complete set of bases of the momentum vectors in the reciprocal space, right. Notice here that the coefficient C will have dimensions of charge square over length square, okay, because this will have a dimension of charge square over length. So this is charge square over length square, and then there is a volume over here. So this is charge square into L square divided by L cube. So you will get charge square over length. So those are the dimensions of the coefficient Ck. This is actually a triple sum, because every k has got 3 components, the kx, ky, kz. So you must sum over all the components. Okay, so this is our expression for the Coulomb expansion. We first consider the case when the momentum vector k is not equal to 0. Now when this is the case, if you multiply both sides by this term, e to the I k prime, so the dummy index over here is k, that is the reason I choose a different wave vector over here, which is k prime, and I multiply both sides by this term. So let us do that. I multiplied e square over rij by this exponential function on both sides, okay. And now you see that the right hand side I can move. These two arguments are very similar, except for the fact that this is k and this is k prime. On the other hand, this is ri minus rj, this is rj minus ri. So if you take the dot product of k minus k prime with ri minus rj, you get an equivalent correspondence over here, okay. So this is your expression that we will now note that there is a minus sign over here, and if you integrate this result, so this term is now integrated over volume. You carry out a volume integration, so you have a volume integration of the right hand side, and now you can see what this volume integration is going to lead you to, because all I have done here is to extract the e square out of the integration symbol, and then this is nothing but the Fourier transform of the Coulomb potential, right. So, you get 4 pi E square into 4 pi over k prime square, k prime because you have a k prime over here. Okay. So, this is the Fourier transform of the Coulomb potential, and our result is that 4 pi E square over k prime square is equal to this integral, but when you look at this volume integral along with the 1 over v, you are essentially looking at the Dirac delta which we have used in the previous class. Okay, we have used this explicit form of the Dirac delta. So, now you have got a Dirac delta and you have to sum over all values of k. So, the only term under the summation k that will survive is the one corresponding to k prime. So, that is your result. So, on the right hand side only Ck prime will survive because of the Dirac delta, and Ck prime is 4 pi E square by k square, k prime square, and you can drop the prime now. So, this is your general expression for the coefficient Ck, which is 4 pi E square over k square, except when k is equal to 0, okay, because when k is equal to 0 this term seems to blow up. So, that we will deal with separately. So, this is our expansion for the Coulomb potential. Okay. This is the Coulomb potential of the ith electron in the field of the jth electron. What is the value of Ck when k is equal to 0? Okay, we have determined the values of Ck in general, but we have to find out what is its value when k is equal to 0. So, what you do is if you integrate this expression, this is your complete result. Okay. We know that you have a Dirac delta on the right side, and for whenever k prime is equal to 0, you put this k prime equal to 0. So, this will be e to the power I k dot Ri minus Rj, because k prime is now set equal to 0. So, this will be delta k minus k prime, but k prime is equal to 0. So, this becomes a delta function again, but not of k minus k prime, but delta of k, because k prime is equal to 0. So, this is our result here, that you have delta of k, and this means that when the only term that will survive under this summation is the term corresponding to k equal to 0, right, which is C0. So, that is your coefficient C0 now. What is C0? What is this? This is nothing but the potential of the ith electron in the field of the jth electron, as if the jth electron is smeared over the whole box. The jth electron is not at a particular location, it is smeared over the whole box. The potential energy of the ith electron due to just one electron, but that one electron is smeared over the whole box at a uniform charge density. So, that is what we get for C0. Now, this is the expression now for the potential energy of the ith electron due to the jth. Okay. Now, what will be the potential energy of the ith electron? How many electrons are there? There are n electrons. So, you have to sum over all the remaining electrons, the potential energy of the ith electron due to all the other electrons, not just the jth one. So, you must sum over j going from 1 through n except for j equal to I. So, this is the net potential energy of the ith electron due to all the other electrons. You have got 1 over v, it is this term, you have got this term which comes here, and you are summing over j going from 1 through n and avoiding j equal to I. And we know what Ck values are. Ck is given by 4 pi e square over k square whenever k is not equal to 0, and whenever k is equal to 0 it is given by this. Okay? So, we have got everything that we need. Alright, so having gotten this is just the potential energy of the ith electron in the field of all the remaining electrons. We have still not considered the gallium potential. We have not considered the positive nuclei. What we do know that if you consider the positive background, okay, then you have various effects coming because of the background Hamiltonian, and there is another part of the Hamiltonian which is the electron background interaction. But we have already found that the k equal to 0 term, okay, cancels the positive gallium. We have discussed this in an earlier class. Okay. So, if you take this for all values of k, but if you leave out the k equal to 0 term, because that is the term which is going to cancel the positive gallium effect, then you have got the potential energy of the ith electron in the field of all the remaining electrons and the positive background. Okay? And that is then given by this expression on the right hand side, inclusive of the summation over k except for the k equal to 0 term, because that is the one which goes into the cancellation of the gallium. Okay? Alright, so this is our potential now, which is the potential energy of the ith electron due to all the remaining electrons and the positive background. Okay, now you have got the potential, and if you have the potential, you can find what is the force acting on it, because force is the negative gradient of the potential. So, let us write the force, which is mass times acceleration, which is mass times the time derivative of the velocity, and this will be the negative gradient of the potential. The potential u is given by this relation at the top. This is the net force which the electron experiences. Of course, if charges are in motion, they will generate magnetic fields, and the magnetic field will in turn exert a force on this charge, which will go as V cross B, that is the Lorentz force, right. So, that is typically a lot weaker than the forces we are considering, and those weaker magnetic forces we are ignoring in this analysis. So, the expression for the acceleration becomes, you have to divide everything by mass. So, you have got a 1 over m coming here and 1 over m coming here. So, you have essentially the negative gradient of the potential. So, you have to take the gradient, the negative gradient of the potential. Now, what is dependent on r? Because gradient will take space derivatives with respect to the coordinates I, and the only thing that depends on I is sitting over here. Okay? The 4 pi e square over mk square does not respond to the gradient operator. So, you have got the gradient operator which I have written in a bracket along with the term for where it really matters. So, this is the acceleration of the ith electron. So, this is still a classical model, and today I am going to discuss the classical model, and then tomorrow we will get into the quantum model. So, now we have to take the gradient now. What is this gradient? Gradient of this term with respect to the ith coordinate is ik, right, and then you have got an exponential function. This I of course is square root of minus 1, okay, and this ri, which is the subscript on the position vector, is referring our discussion to a particular ith electron. So, I am using the symbol I for two things. One is the index of the electron, and the other of course is the square root of minus 1. So, there is, so this is our result for the acceleration of the ith electron, which I write at the top of this slide now. Now, notice that this is a summation over j going from 1 through n, but j equal to I was avoided. On the other hand, if you look at this term which is in the box and analyze this term and ask yourself what would happen to this box. This box is what I will call as a summed. This is something which is being summed over, right? Like the integrand is what gets integrated, a summand is what gets summed up. So what is sitting in this red box is going to be summed up for different values of j going from 1 through n, but we are avoiding j equal to I. So j not equal to I is specified explicitly over here. But what is being summed up is this term which for j equal to I will give you a 0 here. Ri minus rj will go to 0 for j equal to I, because rj minus ri will go to 0. So you get e to the power 0 over here, which is 1, okay, and you are then summing the rest of the vectors. The summand on the right hand side for j equal to I is this, and this is of course 0 because you are summing over all the momentum vectors, and there are as many momentum vectors in one direction as there are in the opposite, which are exactly equal and opposite. You have got the entire Fermi surface, which is a spherical surface, and there are vectors in opposite directions in this Fermi surface, whichever direction you look at, right. So they will all cancel each other, and you have got a vector sum of k summed over k is not equal to 0, and this will give you a null vector, and therefore it really does not matter whether you include j equal to I or you do not include j equal to I, because the term corresponding to j equal to I gives you a 0 anyway. So you are only adding a 0 coming from j equal to I terms, and it really does not matter. So we have no real need to exclude the j equal to I term. So now we write this summation over j going from 1 through n, but we do not specify any further that j equal to I has to be avoided. So this j not equal to I is not written over here. We are letting j equal to I as well, because it really does not matter. Okay. So this is our expression for the acceleration. What is the electron charge density? We had this relation earlier with us. We know that when you integrate this charge density, you get the total number of electrons. We discussed this. We have the Fourier expansion of the charge density in terms of the Fourier components rho k, which in our system of equations is dimensionless. The left hand side has got a dimension of 1 over volume. It is the number per unit volume, and the inverse volume dimension is taken care of by 1 over v over here. So the equation is essentially balanced dimensionally. So these are our expressions for the Fourier expansion of the charge density. The Fourier components can be written in terms of the inverse transforms, right? And this density is nothing but the summation over the delta functions, and if you write this summation symbol, because this is summation over I, this is integration over space, this is a particle index, this is space integration. So these are completely independent operations, so you can write this behind the integration, and then you carry out this integration over here, so that essentially what you will find is that the Fourier component is given by sum over I going from 1 through n, and under this Dirac delta integration, the only term that will survive is e to the minus I k for r equal to ri, because of this delta. R must be equal to ri, otherwise the integral will vanish. So this is the expression for the Fourier component of the charge density. For k equal to 0, you of course get the total number of electrons. Okay. So now let us analyze these expressions further. It is the k not equal to 0 terms which will be involved in the density fluctuations over the average. So, you have got a certain static average charge density which is smeared over the whole space, but then you can have density fluctuations on top of it, and these are the ones which were not included in the Hartree-Fock, if you remember, because the Hartree-Fock approximation is essentially a frozen orbital approximation. You do not consider these density fluctuations in the Hartree-Fock. And the Hartree-Fock, we have also seen, is completely equivalent to what you get from the first order perturbation theory. So, obviously, we are going beyond the perturbative method, we are also going beyond the Hartree-Fock. So, this is our expression for the acceleration of the ith electron. You have got sum over j. We are now admitting j equal to I, it does not matter, and I have simply rewritten these terms. This is just bookkeeping, but I factor this exponential function into e to the I k dot ri term, which is here, and e to the, there is a minus sign here, minus I k dot rj, so that comes over here. So, I have separated these two terms and I have confined the summation over j over here, because this is the only thing which is affected by j. So, what does it tell us? That this term, you have e to the I k dot ri when you sum over I going from 1 through n, and this is exactly the same term, right. This is nothing but the Fourier component rho k, right. So, in the expression for the acceleration, which is the time derivative of the velocity, these terms remain the same. You have got I, you have got sum over k, k not equal to 0, all that is fine. You get k over k square. Here you have got e to the I k dot ri, which is here, and this is nothing but the Fourier component rho k. So, rho k is appearing here. Now, we are developing the equation of motion. Look at this. Now, if you want to develop an equation of motion for the Fourier components, you must take the first derivative, which will give you the velocity, and then you must take the second derivative, which will give you the acceleration. And equation of motion, as we know, is the relationship between position, velocity and acceleration. So, we have to get up to the second time derivative. So, the first time derivative will give you the rho k dot. So, let us do that. So, you have to take the time derivative of this summation. So, rho k dot will give you the time derivative, this is just an exponential function, and then you must take the derivative of the exponent. So, which is I k dot ri, and k is time dependent. So, you will get k dot r dot, which is k dot velocity term. So, this is the time derivative of the Fourier component rho k, right. Now, we can take the second derivative, because then we will be led to the equation of motion. This is all classical. It will be tomorrow that we will discuss the quantum treatment, and the second derivative, according to Newton's law, which is involved in the equation of motion. So, the second derivative of the Fourier component will give you the time derivative of the velocity term, which is rho dot. So, which is minus I summation over I going from 1 through n, which is coming from here. Then you have got the time derivative of the product of these two functions. Okay, there are two functions over here, both have got a time dependent term, Ri is time dependent and the velocity will also be time dependent. Okay, because the velocity of the ith particle depends on time, its time derivative will give you the acceleration of the ith particle, right. So, both of these terms are time dependent, and you will therefore get two terms, the first term times the time derivative of the second plus the time derivative of the first term times the second term. So, you have these two terms now. So, you have got the time derivative of the first term, which is e to the minus I k dot ri times the time derivative of the exponent, which is minus I k I dot ri dot, right. And then the second term has got the first term times the time derivative of the second, which gives you the acceleration of the ith coordinate. So these are the two terms which appear in this equation of motion for the kth Fourier component in the charge density. Now you can write e to the minus I k dot ri common in both, and you have got these two terms. Okay, so that's what you have got. Now it is a very interesting kind of situation now, because look at these terms. Do you recognize some familiar terms in this? If you look at this Ri double dot, this is, we already have this result, and this was expressed in terms of the acceleration of the ith particle, which we obtained just a little while ago. Okay, and this is from a previous slide, just few slides prior to this one, and in this one we have got the acceleration term of the ith electron, for which we obtained this result, and we can plug in this expression over here. Let us do that. So we have got the second derivative of rho k, you have got the first term which is written exactly as it is over here. The second term you have got minus I sum over I going from 1 through n, which is here. Then you have got k dot, and now you have this acceleration of the ith particle, and that, for that we use this right hand side over here, which is put in this beautiful bracket. And then of course you have this e to the minus I k dot ri, which comes here. Alright? Okay. Notice that there is a minus sign over here and a minus sign over here, so that will give you a plus 1 factor, but then notice that there is an I over here and an I over here, so that will give you I square, so you will have a minus 1 popping out of it. So you take care of all of these signs and the I square, so you get a minus sign coming because of the I square. Okay, the first term is written as it is. Now these two minus signs have been taken care of, the I square is taken care of, you have got the 4 pi e square over mv over here, you have got the summation over I going from 1 through n over here, and now you have got the summation over k prime not equal to 0, you have this k dot k prime, right. So that is coming over here in the numerator, you have got k prime square in the denominator, you have got the Fourier component rho k prime, and then you have got the product of these two exponential functions, which gives you I to the power k prime minus k dot ri. Okay. Now let us bring this to the top of the next slide. It's the same, essentially the same expression. And now this summation is a summation over k prime, and I break this summation into two parts, one corresponding to k prime equal to k, and the remaining set of terms corresponding to k prime not equal to k, because in some cases k prime will be equal to k. So that is the term I separate out. So there are only these two terms in the equation in the first row over here, but the summation over k prime is written with one of the terms, the term corresponding to k prime equal to k separately, and the other terms in which k prime is not equal to k. In both cases k prime is not equal to 0, right. So this is the term corresponding to k prime equal to k, and this is the term corresponding to k prime not equal to k. So now what were two terms in the first expression appear as three terms, because this summation is now separated to write one term explicitly for k prime equal to k, and these are the remaining terms. So these are the three terms now. Let us take these three terms, and you notice that this k dot k by k square is nothing but unity, because this will give you k square by k square, right. Then if you look at this sum over here, e to the power 0 is 1, So you are adding 1 to itself n times, so you will get a factor of the total number of electrons over here, okay, which means that the next time you write this result, you can drop this k dot k by k square, because it is just multiplying everything by 1, and instead of this factor sum over I going from 1 through n e to the power 0, you can write the total number of electrons. So let us do that, which I have written over here. I have dropped this factor of unity and I have written n over here. So this term becomes minus 1 over v 4 pi n e square. This is the n and this is the e square and this is the m, and then this is the rho k, which is the Fourier component, right? And the third term is written just the way as it is, okay? So let us take this term now to the top of the next slide, which is here. All right, what is this? This is the equation of motion for density fluctuations of the Fourier component k. Now this looks a little messy, but we will see that it can be really simplified, because if you now carry out this summation over I, okay, where does I appear? I appears only over here. So carry out this summation over I going from 1 through n, and then you have got this summation, okay. What does it give you? That looks very much like this, right? What you have in this beautiful bracket is just a term similar to this, except that you have got an argument which is k prime minus k, and that will give you the Fourier component k minus k prime. So this is the Fourier component rho k, this is the Fourier component rho k, and this will be the rho k minus k prime component, right? Now this is the equation of motion for the Fourier component. This is the second derivative of with respect to time of the Fourier component rho k, and this has got all of these terms 1, 2, 3. Now this looks messy, but we are going to develop an approximation, which is the random phase approximation, which will help us write this equation in a very simple form. You can already see what is the most simple form that you can extract from this. If you were a mathematician and you were looking for what terms look familiar, you have got acceleration on the left hand side and you have got one term on the right hand side which is proportional to the displacement itself, which is this term, okay. The second time derivative is proportional negative to the displacement rho, right. Now that is the situation you have for a simple harmonic oscillator, where what you have is not that just that, but you have additional terms. Now what if these other terms don't matter? If you can find some way of throwing them out, not just because you don't want to solve such a complicated mathematical equation, but because there is some good physical reason for it. And in fact, as you might begin to suspect, there is in fact a good physical reason for this, which I will be discussing in the next class. But what this reason will help you do is to ignore these terms. These terms you will be able to ignore because of an approximation which is the random phase approximation, and you will find some additional reason to ignore this term as well. And then what you will be left with is the second time derivative of rho k, which is directly proportional to the displacement rho k itself and always directed inward, okay, which is what you have in a simple harmonic oscillator. So it is just the equation of motion for a simple harmonic oscillator. F is equal to minus kx for a one-dimensional linear harmonic oscillator. K is a spring constant. So that is precisely the equation that you will get. So Bowman-Pines found a very good reason to ignore these terms, and I will discuss this reason in the next class in some details, and they found a good reason why this term can be ignored. Notice that this is a quadratic term. Okay, there is only one linear term in rho over here. There are two terms in rho. So, this term that you are going to ignore is the quadratic term in rho, and the heart of this approximation is this linearization process. The nonlinear term is thrown out. So, the heart of the RPA lies in this linearization process. So, this is the approximation which gets to be known as the random phase approximation, and you can already see that the phases in picture are coming from these phases, because you have got these exponential functions. So, e to the I theta, theta is the phase, right. So, it is the sum of cosine and sine terms, and you have got these quadratic terms. So, they will cancel each other because of the cancellation of the random phases, but I will discuss this in some details in the next class. If there is any question on what we have done so far in today's class, I will be happy to take it. Questions? Essentially what we did was a classical model. We have really not done any quantum theory. Okay? What we did was the expression of the charge density, resolved it in Fourier components, found out the position vector of the ith electron, found its velocity, found its acceleration. Okay? And using that, we set up the equation of motion for the density fluctuations. Okay? So, it is a classical model or a semi-classical model if you like, because we did use the Hamiltonian earlier in some part of the discussion. So, it is like semi-classical but mostly classical model. We are still using the equation of motion, we are still using Newton's laws, F equal to ma. So, this is all classical argument, but then in the next class we will also get into the quantum method, which was also developed by Bowman-Pines. So, if there is any question, I will be happy to take. Otherwise, thank you for today, and we will meet at the next class.